In the last video, we saw how a binary operation can be commutative. Next, we have something else, associativity. Let A be a set, non-empty set of course in this context, and let star be a binary operation on A. Then we say that star is associative if this equation is true. A star B star C equals A star B star C for all A, B and C in A. Do not forget this part. This needs to be true for any choice of three elements A, B and C in A. And by three elements, I don't mean three distinct elements, okay? There may be repetitions here. A and B may be equal, anything can happen. The point here is that if this equation is true for any choices of A, B and C in A, then we will say that star is an associative binary operation. You are already familiar with associative operations, I mean their examples. For example, addition and multiplication are associative operations on the set of real numbers. But not every operation is associative. Subtraction, for example, is not associative, which you can see from this. If you bracket this combination of these three ones, note that here I state that elements can be repeated. So here all the three of them are equal, they are 1. But if you bracket them this way, you get one real number, bracketing them the other way, you get another real number. So this one is not associative. Similarly, division, which is a binary operation on the set of all non-zero real numbers, is also not associative. It's pretty easy to come up with one such non-example for division. So you try that. Associativity allows us to get rid of brackets when considering a combination of elements like this, where there are finitely many elements, of course, but not necessarily 3. Any finite number of n number of elements. So say A is a non-empty set on which we have this binary operation star, which is associative, then this product has a definite meaning. Okay, I am calling it product because it looks like product. You may have plus here, but in general such a combination is called product. So this has definite meaning. Let's see the simplest case first. Suppose n is 3. So here you have A1 star A2 star A3. What does associativity tell you? It tells you that no matter how you bracket this product, whether you bracket A1 and A2 together, that is keeping them together, and outside you keep A3, or whether you bracket A2 and A3 together, keeping A1 outside, you are going to get the same result. What is the significance of putting brackets? It indicates in what order you have to perform the calculation. If you are bracketing A1 and A2, then you first calculate A1 star A2. Then with that result you calculate next star A3. Whereas if you bracket A2 and A3, then first you calculate A2 star A3, then with that you take the star of A1. In general they should be different, but if the operation is associative, then they are the same. And this extends to any finite number of elements. Here also you can imagine that as the number of elements increases, the number of ways of bracketing this product also increases. But because of associativity, no matter how you bracket this product, you are going to get the same element. Okay, so this is one advantage. And you actually use it all the time. I mean, you write things like this, right, without using brackets. It does not matter whether you first calculate 1 plus 2 and then add that to 3, or whether you add 1 to 2 plus 3, you are going to get 6. In that first way of bracketing, you get 3 plus 3, that is 6. In the second way of bracketing, you get 1 plus 5, that is also 6. This convenient property of associativity, which we use all the time for addition and also multiplication, is not of course present for every binary operation. Consider this example. Let star be this binary operation on R, where for two real numbers A and B, we define A star B to be equal to A plus 2B. If I am remembering correctly, we have already considered this to show that not every binary operation is commutative. Yes, I think so. And this is also not associative, which you can see here. We consider 0, 1 and 1 in place of A, B and C in that associativity equation. Say you calculate this. What is 0 star 1? 0 star 1 is 0 plus 2 times 1. That means it's 2. And the 2 star 1 is 2 plus 2 times 1, that is 4. Whereas if you do this calculation, 0 star 1 star 1, then you can easily see that this is 6. They are not equal. Next, you consider this simple fact about addition and multiplication of real numbers. For any real number a plus 0 equals 0 plus a, which equals a. This is something we already know. Similarly, for any non-zero real number a times 1 equals 1 times a equals a. So do you see that there is a kind of sameness to these two situations, in the sense that these elements 0 and 1 do not affect these operations. 0 has no effect on a when addition is involved, and that too no matter which order you choose to add the two things. Similarly, 1 has no effect on a when multiplication is involved. When this happens, we say that 0 is an identity element or an identity for the operation plus, and 1 is an identity element or identity for the operation multiplication. And this prompts the next definition. This definition, let A be a set and star be a binary operation on A. An element E in A is called an identity or identity element for star if these conditions are true. A star E equals E star A equals A for all elements A in A. This E in that sense is like this 0 here or like this 1 here. Now, there is something about this definition that you should know. Given any binary operation, it's not necessary that such an element E will exist. That is one thing. And the other thing is that even when an E exists, there may be multiple such elements. So neither existence nor uniqueness is guaranteed. In these cases, they exist and they are unique, but that's not the case always. As a non-example, you can consider this one. Consider the binary operation of subtraction on the set of real numbers. Our claim is that there is no identity element for subtraction, but forcefully suppose there is an identity, say E in R, for the operation of subtraction. Then A minus E should be equal to E minus A. That means now the star is minus. That should be equal to A for all real numbers A in R. In particular, for A equal to 0 also this should be true. That means 0 minus E should be equal to E minus 0. That should be equal to 0, which however gives you E equal to 0. That means E should be 0 if this is to be true. But then this should also be true for all A in R. So now you can take A equal to 1. But with A equal to 1 and E equal to 0, this equation is not satisfied. In fact, you do not have equality anywhere. 1 minus 0 is not equal to 0 minus 1. 0 minus 1 is also not equal to 0. So that means actually no such element can exist. That is, subtraction lacks an identity element. Sometimes an operation which is known to have an identity element might fail to have an identity anymore if you change things slightly. We know, for example, that addition of real numbers has the identity element 0. But if we change the operation and consider addition on the set of natural numbers, then, but wait, before you see anything else, Is it really a binary operation on n? Yes, because if you take two natural numbers, then their sum is a unique natural number. That is why. Do not take anything for granted. Okay, unless you are absolutely sure that yes, this is the case, do not move forward. Now we are saying that there is no identity element for this addition. Why? In fact, we have written that here there exists no e in n such that a plus e equals e plus a, which equals a for all a in n. That is because the e that we normally have with plus is 0, which however is no longer present in n. You go back to the original definition of identity element and see all the parts carefully. The identity element needs to be an element in the set. Okay, otherwise it cannot be of course considered. The 0 is not present in n. So, in spite of it being addition, still in this case there is no identity element. That is because addition is not just simply addition. Addition of what? This is addition of natural numbers, that is addition of real numbers. Strictly speaking, these are two different binary operations. Next, we consider another known fact, two facts actually. We know that for each real number a, there exists its negative such that the sum of the number and its negative in any one of the two orders is equal to 0. Where what is 0? 0 is the identity element for addition. Just like that, for any non-zero real number a, there is its reciprocal, which is also a non-zero real number, so that the product of the number and its reciprocal in both the orders is equal to 1, where 1 is the identity for the operation of multiplication. And this observation prompts the next definition. This definition, again the same setup, let a be a set and star be a binary operation on a. But now the extra thing is that with an identity element e in a. We are mentioning this because as we noted that not every binary operation has an identity element. Say this one has. Then an element a in a will be called invertible. That is, we can invert it provided, with respect to star of course, provided there exists an element b in a such that a star b equals b star a equals that identity e. And if such an element b exists for a, then b will be called an inverse of a. Now looking at the source of this definition, it becomes clear what we are talking about here. In this case, actually we considered multiplication on the set of non-zero real numbers. But for a moment, let's think of the set of all real numbers. Is multiplication a binary operation on the set of all real numbers including 0? Yes, of course. And does that operation have an identity element? Yes, 1. Now let's choose a real number, a specific one, say 2. Okay, 2 is the real number. You imagine 2 in place of a. For that 2, do you have a b in the set of real numbers such that a times, 2 times b equals b times 2 equals 1? Yes, and that b is 1 divided by 2. So that means 1 divided by 2 is an inverse of 2 with respect to multiplication. Here, just like we have written with respect to star, with respect to multiplication. Now there is a possible confusion here. That is why I have put a star here. We are saying that star is a binary operation on a with an identity element n, not the. There is an identity element, but the definition of identity element does not immediately make it clear whether it is unique, whenever it exists. Actually, that is the case. But there we noted that maybe possibly if a binary operation has one identity element, maybe there are others. So which one should we use here? But this confusion is actually not a confusion, because if an E exists, then that is the only E which we can prove. So like that, there is no confusion. If there is an E, then that is the only E which should be used here. So we just now saw that for the operation of multiplication on the set of real numbers, 2 is invertible. Just like that, you can understand that every non-zero real number is invertible with respect to multiplication, with its reciprocal as its inverse. But what about 0? 0 is not invertible. There exists no real number which you can multiply with 0 and get 1. You multiply 0 with any real number, you will get 0. You will never get 1. So that is the only element in R which is not invertible with respect to multiplication. All non-zero elements are invertible. Let's consider another example. Here things will change drastically. It will be quite different from what we saw just now for multiplication and real numbers. We are again considering multiplication, but this time on the set of natural numbers. It is a binary operation, because if you multiply two natural numbers, you get a unique natural number. And there is an identity element also, because the one that normally is the identity element for multiplication is present in n. However, if you look carefully, the element 2 is not invertible. If you multiply any natural number with 2, you will get something, but you will never get 1. That is because the normal inverse, the reciprocal of 2, is not in n. The inverse should be inside n. Inside n means inside the set. You see, B should be in A. Then only we say that inverse exists and the element A is invertible. 2 is not invertible, and this immediately makes it clear that actually no natural number is invertible other than 1 itself. 1 is invertible. If A is 1, then you can take B also to be 1. 1 is its own inverse. So this situation is exactly what that one is not. There, every real number except 0 is invertible. Here, every natural number except 1 is not invertible. And before I end the video, I need to mention, I forgot that. Just now I said that whenever a binary operation has an identity element, then it can be proved that it is unique, provided it is an associative binary operation. Okay, I forgot to say that.